Hello all, I want to welcome you back to our lecture series. Today we'll be talking about properties of solutions. Particularly, we'll focus on osmosis. There are other properties of solutions, but our main focus at the level of this class will be on osmosis. Alright, and thank you for joining once again. Let us take it off from there. As usual, I have a beautiful quote for you. I'm just going to read it. I'm not going to say anything about it. It says, "There is no education like adversity." Benjamin Disraeli. Let's move immediately. Now, the learning objectives or the learning goals in this class is that at the end of this class, we'll be able to differentiate between electrolytes and non-electrolyte. 2, we're going to understand the term osmolarity, and then we're going to do calculations with osmolarity. And finally, we'll describe the dialysis process as it relates to osmosis. What's the relationship? What principle does dialysis operate? And we know that is osmosis, but that will be explained at the end of this class. All right, so let's take it off from there immediately. Solution properties. Now, when substances dissolve in water, they begin to have different properties. That is what we mean by solution properties. So when, okay, let me give you 2 examples. Now, if I have 2 things here, assuming I have sodium chloride, which is a solid in its natural state, I dissolve it in water. And I also have glucose, C6H12O6. I also dissolve it in water. Now, if I dissolve this in water and dissolve this in water, let's see what happens here. Both of them are going to dissolve because both of the glucose is a polar solvent. Sodium chloride is ionic, so it's going to dissolve. Now, this one will dissolve and break apart into ions because it's an ionic compound while it is hydrated. On the other hand, glucose here is going to dissolve in water, but it's not going to break apart. It's just going to become glucose molecule and becomes aqueous. This is what we mean by the properties of solutions. So solutions can dissolve in water and become different stuff. Now, this guy started with 1 mole. And here I ended up with another 1 mole plus another 1 mole. So this becomes 2 mole. Whereas this started with 1 mole and ended up with 1 mole. So the properties in solution is not going to be exactly the same. That takes us to what we call electrolyte. Electrolytes are such substances that when dissolved in water, they begin to conduct electricity. And most of those substances that do this are either polar compound or ionic compound. However, both of them will have to do what? They have to ionize in water. They have to ionize in water, meaning they will release their ion. They will release ions when dissolved in water. On the other hand, non-electrolyte are those substances, of course, like I said, like glucose. Remember, this is an electrolyte. Okay, let me just write that. This is electrolyte. On the other hand, substances like glucose will do what? Dissolve in water like we saw, aqueous, from solid. Okay, remember this is solid to aqueous. But it will not conduct electricity because it does not ionize. And because it does not release ions, it remains as a polar covalent compound as it were. And therefore, it is a non-electrolyte. It is a non. So solutes that when dissolved in water forms a solution that does not conduct electricity. So these ones will conduct electricity because of these charges, but this thing has no apparent charge and therefore it will not conduct electricity. So on that note, we can divide electrolyte into strong electrolyte and weak electrolyte. Now, strong electrolyte are those ones that dissociate completely. Like I said, like most ionic compounds that are soluble will dissociate completely in solution and release their charged ions, because it is these charged ions that are the carrier of electricity. They form strong conducting solution. Good examples is like hydrochloric acid, which is a polar compound, but because it releases hydrogen ion and chloride ion, it is a good conductor. Calcium nitrate as well. Weak electrolyte will only dissociate only slightly. They are just not ready to give up as much ions as possible. They only do that slightly. So they still dissolve, but they remain in the intact, uncharged form mainly. A good example is acetic acid. So this is acetic acid. Acetic acid is actually an organic acid. It can release this hydrogen. However, look at what happens here. I'm going to write 2 arrows. Now, the arrow with which it's going to release the hydrogen is small because it doesn't want to do that. However, it wants to remain, this is what we call the dominant form. It wants to remain as and uncharged form, and as a result, it is what? A weak electrolyte, because it is not ready to give up as much charge as possible that will make it to be a strong electrolyte. So let's now take it to osmosis. Now, osmosis is just defined as the movement of particles from region where they are crowded, the region of where you have too many of them, to a region where you have them in few quantity. That's what we mean by osmosis. Osmosis is simply the same thing with diffusion, because osmosis follows the concentration gradient. It still goes from high to low. And high to low simply means concentration, there should be that change in concentration difference. That's what I mean by concentration gradient. Let me say concentration gradient or difference. It has to be from high to low concentration. It can be any type of particle, can be molecules, can be ions, but any type of particle moving from region of higher concentration to region of lower concentration. Something is very important, across a semi-permeable membrane. This is the difference between osmosis and diffusion. Diffusion simply means movement of particle from region of high to region of low concentration. It does not go through a special membrane. But in this case, it is a special case of diffusion involving this what? Semi-permeable membrane. Now, this semi-permeable membrane is a gatekeeper. It is a gatekeeper that allows some molecules that are small enough to pass through while not allowing others to pass through. So a membrane with tiny pores that are big enough that small particles can pass through them, but not big enough to allow the passage of larger molecules. So it is the gatekeeper. It is the bouncer of this party in the cells. It does not want some unwanted, uninvited guys to come in. So, and the resistance to this flow, the resistance to osmosis from occurring is what we call osmotic pressure. So osmotic pressure is the pressure that prevents osmosis from occurring, and that is what we call osmotic pressure. And the higher the concentration gradient, the higher that particular pressure. So that is what we call osmotic pressure. And we're going to see how to quantify it. But before that time, let us look at what happens here. Now, this is a typical case of osmosis. Now, this is the initial condition. In the initial condition, this is a semi-permeable membrane. Like I said, a semi-permeable membrane is any membrane that will allow some stuff to pass while preventing others to pass. Now, this semi-permeable membrane is only permeable to water. This guy is only permeable to water molecule, and therefore it's going to only allow water now. But if you look at this now, across this semi-permeable membrane, which is acting as a wall, on this side you have a sugar solution, on this side you have pure water. Now, in between these two places, water can only pass. What it means that a sugar solution is this sugar dissolved in water. So at least the sugar solution means it will have less water than this side. So if you look at it, here now has less water. Now pure water has 100% water, so this has more water. Now, what is osmosis? Like I told you, osmosis simply means it's going to go across a semi-permeable membrane, but it has to be from high to what? Low. It has to be from, this is osmosis, it has to be from high to what? Low. Across this semi-permeable, this is the semi-permeable membrane. Good. So this is the semi-permeable membrane. So it's going to move from high, where you have more of it, to where you have low of it. So if you look at this now, there is more water to the left side of this barrier. The barrier is the semi-permeable, the permeable membrane, or you can say the semi-permeable membrane. Now, there is more water here. So it's logical that water is going to move across its gradient from place where it is high to place where it's. So what do you start noticing? You start noticing that the size of this side will begin to rise. And at a point whereby the concentration becomes equal on both sides of the wall. And at that time, osmosis is going to stop. And if you can measure the height of this rise from the height of this rise, the difference between the height of water on both sides, that measures the height, and this height is actually proportional to what we call the osmotic pressure. And this is how osmosis actually takes place. And we're going to see the application of this, because this happens in almost every cell, because most cells in our body are bounded by the cell membrane, and the cell membrane is a very good osmotic membrane that allows some particles to pass and then prevents others from passing out as well. So we're going to see this as we move on. So now osmotic pressure and osmolarity. Osmolarity is actually directly related to osmotic pressure, and we can use that to quantify the concentration. As we can use that to quantify osmotic pressure as a concentration of the solute that we find inside the cell or out of the cell or in solution. So it is a product. Now let's define it this way. Osmolarity is simply a product of the number of species produced when a substance or when a solute dissolves in water times its molarity. Of course, molarity again is measured. Remember, M means molarity, and molarity is measured in what? In moles per liter, or you can say capital M, always. So I is the number of those particles that is obtained when 1 mole of that solute particularly dissolves. And of course, M is the molarity. Now let me show you this. Now, like the example I had before, when sodium chloride breaks apart in water, it gives you sodium ion plus chloride ion. What it means is that this is 1 mole of it. When 1 mole of this breaks, it gives you 1 mole of, and 1, so the total of mole it gives you is 2 moles. And this is what we call I. This I is, so we can say that the I of sodium chloride is equal to 2. Because when it breaks apart, 1 mole of it is going to yield 2 particles or 2 ions of 1 mole of sodium ion and 1 mole of chloride ion. On the other hand, if you have glucose, glucose is what? Is a non-electrolyte. It does not ionize. It will still give you C6H12 O6 aqueous. So the I of glucose is just going to give us 1 because it does not ionize. So this thing makes a lot of difference when solutions dissolve in water. Their properties now begin to be different because of the ability either to break apart or not to break apart in solution of water. Let's now do our first problem here. It says, what is the osmolarity of 2.5 molar solution of calcium chloride? Calcium chloride is an ionic compound, of course. Most ionic compounds will do what? Will dissolve in water and dissociate. So if that be the case, we'll first of all write what? The dissociation equation of this guy. So writing it, this is solid. Let's assume it's solid. And then we put water in it. And when it breaks apart, of course, it's going to form calcium ion, which is aqueous, plus chloride ion. How many chloride do we have here? This is 2. So you have to balance the equation to be chloride ion. So what that simply means is that now 1 mole of calcium chloride breaks apart. It produces 1 mole of this plus 2 moles of this. And that's a total of what? 3. So you can say that the I of this guy is equal to 3. This I is actually called something, but we don't need to say that name in this class. Just to have it as I. Alright. So the I of this. Then what we do next, remember, we said the osmolarity is equal to the I value times the molarity of this. The molarity will be given. If the molarity is not given and the mass is given and the volume is given, you can use the mass and the volume to calculate the molarity. So here now we're almost done. What are we going to do? We're going to say I is 3 times the molarity. The molarity here is what? 2.5 times 2.5. And when you multiply both of those, it's going to give you 7.5. The unit of osmolarity is osmol. And I tend to write it very fast so that students will not be confused in thinking that it is O. Alright? So the unit of osmolarity is osmol. Of course, that is how this is done. Let's get to the next problem. The next problem is, what is the osmolarity of 2.5 molar glucose solution? Yes, it gives you glucose again. Remember what I said. When glucose dissolves in water, it is polar compound, but it's not ionic. Therefore, it is not going to break apart. The only polar substances that break apart are the acids. Any other polar substance cannot break apart. So this will give you, if you put water on inside this, it will still just give you, it naturally as a solid, it will still give you this, but aqueous. So what that simply means, you start with 1, end up with 1 mole. So the I value is going to give you what? 1. So the osmolarity in this case will just be, we're going to take this 1 times 2.5. And this will give us 2.5 osmol. That is, you look at that. Now, the same concentration of solute, 2.5 molar and 2.5, you find out that of calcium chloride gives you 7.5 osmol, and this gives you 2.5 osmol. So if you dissolve both of them in water, the same quantity in water, the osmolarity, or which is proportional to the concentration, will be higher in calcium chloride than in glucose. That is an important thing to recognize at this juncture. Let's have some more challenging problems here. It says, what is the osmolarity of a solution formed from 24.22 grams of sodium carbonate in 500 ml of water? Remember, osmolarity, for it to work, you must have to find the I, and you must have to multiply by osmolarity. But we don't have osmolarity here. What do? We find osmolarity by what we are given. We have the mass, we have a volume, we can do the molarity by first finding the mole. However, I'm going to do this in a long swoop. So first thing we're going to do here is what? We're going to calculate the molarity. That's what we do, calculate the molarity. And in doing that, now I want to calculate the molar mass. What's the molar mass of this guy? The molar mass of sodium carbonate will be, there are two carbons, 22.99 is carbon plus, sodium. There are two sodium atoms, 2.22.9 plus, carbon is 1, 12.01 plus, oxygen is 3 times 16.00, and that will give us 105.99 grams per mole. Having done that, then let's calculate the molarity. So that's what we're looking for. So we're going to start with 24.22 grams of this guy. Convert it to mole first. We know that 1 mole of this guy is equal to the equivalent to the molar mass, 105.99 grams. Now, if you look at this, gram cancel gram, but that's not what we're looking for. We want to convert it to what? Moles per liter. Remember, molarity means moles over liter. Let's put it that way. Means moles over liter. Now, let's keep going. Now, but we have something we can do. Now, we want it to be, we have our moles on top. The volume of the liters has to be below. But what we have is 500 mils. Since I didn't convert it, I'm going to do, so I'm going to say, I'm going to flip this over 500 mils because the volume has to be under for this formula to work. Now, but nothing can cancel. But if I want to eliminate my mils, what do? I can use my liter. 100 mils will give you 1 liter. If you look at this will cancel this, and you're left with moles per liter. And when you put this in your calculator, you're going to get 0.457 moles per liter. Or you can say 0.457 molar. Doesn't matter the one you use. And now, having gotten this, we're close to it, but we're not done. We need to write the dissociation reaction for this guy. Now, when this guy breaks in water, what do we form? Now, there are 2 atoms of sodium, so you're going to have 2 sodium ions because this is very soluble. It's an unique compound, and this is group 1 element. Any group 1 metal will always be soluble, no matter what the salt is. Sodium ion plus, of course, this is aqueous, plus carbonate ion is just 2 minus. You remember this. So what that simply means is that we have 2 plus, we have 1 here. So the I value is going to be equal to what? 3. Now, what are we going to do? We put it. So our osmolarity, of course, is going to be, our I value is 3 times, you multiply by 0.457. And this will give us 1.37 osmol. That is how you do this problem. Feel free to pause this, pause the video, try out these problems yourself, and always come back to check them for comprehension. Now, again, another problem. Now, this one gives us now the concentration in volume, in weight per volume, and wants us to calculate the molarity of sodium phosphate. Now, we're going to still follow the same process. What happens is that we're going to convert. Remember when we did this, I think that was in the last lecture, we were able to convert from volume, percentage volume by volume, to molarity. That's what we're going to do here now. But first, we have to calculate the molar mass of this guy. So the molar mass of this guy is going to be, let's do it. Sodium is 3 atoms, so I'm going to 22.99 plus phosphorus is 30.97 plus, there are 4 oxygen here, so 4 times 16.00. And this is going to give us 163.94 grams per mole. Now remember again, just let's remember that anytime we have, remember this, that we assume that the unit of percentage weight by volume is going to be grams over 100 mils. Don't forget this. That's usually the assumption. So going from that assumption, let's start. So it's going to be, we're going to do 0.79 grams over 100 mils. That's the assumption. Whenever we have weight per volume concentration. Now we're going to start eliminating. First, I want to eliminate the mils and put liters. To do that, there is 1,000 mils for every 1 liter, and therefore my mils is gone. And then what else? I can eliminate gram by using molar mass. That's the next thing. The molar mass. So to eliminate gram, what it means is that the gram has to be below. So that means it's going to be a mole will give us 163.94 grams. Grams cancels grams. And if you look at that, we have moles per liter. We have it done. So this is going to give you 0.048 moles per liter. It can be moles over liter or 0.048 molar. Now, having done that, what next do? We need to write the dissociation reaction for sodium phosphate. Remember, in that place, sodium has 3 atoms, so it's going to be 3 sodium ion plus phosphate is just 1. And remember, phosphate is just 3. I tell students, it is good you try to write the dissociation equation before you do the problem. So let's calculate. Here now, there are 3 of these plus 1 of these. So this is going to give us equal to what? 4. There are 4 particles. When sodium phosphate dissolved in water, it produces 4 particles of ions. And then what do we do? The osmolarity then is going to be 4 times, what is the concentration? 0.048. And this is going to give us 0.19 osmol. And that is how we do this problem. So what matters in this problem is to follow this concept one after the other, patiently working them through. You're going to get there with the knowledge of concentration of solutions. You finally get there as well. Problem 5. We're getting close to an end. In problem 5, this one I made it. This is a problem involving osmosis and semi-permeable membrane. It's a predict the direction of water flow. Remember, you have to first of all, in each of them, calculate the osmolarity. It is the osmolarity, not just the molarity, that determines which side has more particles. And hence, the side that has more particles will always be the side that is more concentrated. So you have to watch out for that. It says predict the direction of water flow. Consider that both vessels A and B are separated by a semi-permeable membrane. So this is the semi-permeable membrane. Semi-permeable membrane. Now, that is only permeable to water. In the first case, let's see. It says 1 mole glucose, 1 mole, 5 mole glucose. Now, 1 mole glucose, 5 mole glucose. If you want to calculate, remember, glucose is non-electrolyte. So, assuming you want to do the osmolarity is going to be the I is 1 times 1. This is going to give you 1. This one will give you what? This one will give you I is still 1. 1 times 5. This will give you 5 osmol. If I don't separate this osmol from that, you're gonna think it's 50. So this is 5 osmol. This is 1 osmol. So therefore, which side has more water? The side that has more water is the one that is least concentrated. And what that simply means is that osmosis means from region of what? More to less. Water is going to move from where it is more water, which is this. So this is more water. You can say more water to less. This is less. Therefore, it's going to move from A to B. That is exactly how you do that problem. Let's go to the second one. Here, 1 mole of calcium chloride and 1 mole of, remember again, 1 mole of glucose. Glucose, the osmolarity is just going to be 1. It doesn't break, so it's going to be 1 times 1 equal to 1 osmol. This one will break apart into potassium chloride plus chloride ion. So the distance is 2. So it's going to be 2 times 1. It will give you 2 osmol. So if this gives you 2 osmol, this gives you 1 osmol. The implication of that is that there is more water on this side that just gave you 1 osmol. And that has more water. And water is going to move from region of high concentration to region of low concentration. So it's going to be moving from this to this way. So we're going to say it's going to be moving from B to A. From B to A. We go to the next one. Now this one says 1 mole of both of these guys. Remember again, this breaks apart, gives us 2 particles. So this is going to be 2 times 1. This is going to give you 2 osmol. This one will break apart into 1 carbonate ion and this. So this is going to give you 3 particles. So 3 particles, 3 times 1 will give you 3 osmol. The implication of this is, remember, this is the unit. Let me just be circling it so that you don't mix it up. Remember, the implication of this is that This has high osmolarity. Potassium carbonate means that there's more water on the A side because it has less concentration. So the water is going to move from this side to this side. So again, this is going to be from A to what? B. And then for the last one, if you look at this, if potassium chloride breaks apart, it's going to break apart into one potassium ion and one chloride ion. The same thing here, this is going to be 2 as well because this is one sodium chloride and one chloride ion. And now their concentration is the same. Their osmolarity is going to be the same. So this is going to be 2 times 1 will give you 2 osmol. This is also 2 times 1 will give you 2 osmol. Remember, the osmol is the concentration. I'll keep covering that. So since there's no difference in concentration, none of them will move. So there will be no movement. There will be no movement. Or you can say the rate of movement is equal. So none of them will rise. The rate of movement of this will be equal to the net, and that will cancel each other. So you say no movement at the end of the day. And that is how you do those problems. Now, we now look at direct application of osmosis. The most important application of osmosis has been in treatment of kidney diseases, particularly renal failure. When the kidney cannot perform its functions anymore, when its functions has gone below 15%. If the kidney goes below 15% of functional capacity, the person has to be on dialysis. So dialysis is just application of osmosis, because remember, the kidney cells are made up of membranes. These membranes are semi-permeable. So it's a process in which solvent molecules, other small molecules, hydrated monatomic ions pass through a solution through an osmotic membrane. This osmotic membrane will allow these small particles, but will not allow colloids, large molecules, or large polyatomic ions. Good examples is like the proteins, albumin, and the globulin. The proteins will not pass through. These are proteins. They will not pass through, and some other bigger molecules will not pass through. It is used to do what? To separate small particles from colloid and clean the blood of people who have kidney malfunction. Now look at what happens here. Now look at this is a very good example of what we're going to see. Now this is a buffer solution. Now initially at the start of this cellophane bag contains some nutrient. Let me say nutrient. It has sodium chloride. It also has proteins and a couple of other stuff inside it. So it is really very concentrated inside that. That's a concentrated solution. Now what happens here? At the start, this is how you started it. After some time, some small molecules that are permeable to this, like sodium ions, like chloride ions, like glucose and other stuff, are now going to permeate and get inside this place. And when they get inside this place, they keep moving. At the point, at equilibrium, the rate of movement of these guys will be equal to the rate of ones that are moving out. And then at this point, the concentration inside and outside becomes equal. And at that point, no net movement again. So this is what we call, this is applied when people kidney cannot function very well, to clean their blood and make sure that those waste that they needed to remove through the kidney is actually removed through this process. This is a very good invention and a very good application that saves lives in the medical field. Finally, the last thing we're going to be talking about today is tonicity and red blood cell. Tonicity is a term used to describe the movement of water molecule through the red blood cell. This means red blood cell when it is placed in different concentrations. Red blood cell when it is placed in different concentrations of solutions. Now, what happens in this case? If you see what happens, this is very graphic. And you see what happens now. A hypertonic solution is a solution that has high concentration of solute than the red blood cells. So when you put a red blood cell inside this solution, what is happening there? Now remember, we said this is a concentrated solution. It has a higher concentration of solute than inside the red blood cells. Now, what that simply means is that outside the cell has less water because it is more concentrated. Less water means that this side is concentrated. It is very concentrated. That's why it has less water. Now, the implication is that inside the red blood cell itself now has more water. So inside of the red blood cell, okay, let me take here. Inside of it now has what? Has more water. Now, what is going to happen? Something is going to begin to happen. Yes, because water is going to move from where you have more water to where you have what? Less water. And that is osmosis. So now water will begin to leave from region of high concentration, which is inside the red blood cell, to outside, to equilibrate. And as that is happening, the red blood cells begin to lose water and begins to shrink. And when it shrinks, we use the term plasmolysis. We say that the red blood cell has plasmolized. And this occurs when a red blood cell is placed in a hypotonic solution, because it begins to draw away that water, because water is moving from a region of high concentration to region of lower concentration. Now, this is opposite of what is happening at this point. In hypotonic solution, what do we have here? Now, a red blood cell is placed in a solution that has lower concentration of solute when compared to the inside. The implication is that now the outside will have more water. The solution will have more water, whereas the inside of red blood cell will have what? Less water. Again, remember, what is osmosis? From region of more to region of what? Less. So water will begin to move from outside to inside, like shown in these two arrows. And as water begins to move inside the red blood cells, unusually, it begins to absorb this water, begins to what? Grow, begins to swell, at the point it can actually burst. And when it bursts, we say hemolysis has occurred. It's hemolysis, because it will swell at a point whereby it bursts, and then at that point it begins to release its contents. That's what we call hemolysis. Hemolysis means breaking of blood. Hemo means blood. Lysis means breakage. Plasmolysis means shrinking or crenation. However, in a typical environment, the concentration of blood, the concentration of solute inside the red blood cell should be equal to the ones outside the red blood cell. When that kind of condition exists, we say that solution is an isotonic solution. When red blood cells have been placed in a solution with the same concentration in it. In that case, the amount of water going in and the amount of water leaving is the same. So both of in this thermal equilibrium, they can be equal, and there will be no net movement of water. So this is what you have in a normal cell, and this is how the body wants to exist. But in some cases of pathology or diseases, it can lead to someone's cell being in these two other different types of situation that is not ideal. So the ideal situation is the isotonic situation. The cells want to be battered in solutions that have the same concentrations with them. And at this point and on that juncture, we've ended this particular module and this particular class. Thank you once again for listening. I will see you in the next class, and bye.